Hello! We learned 3 numerical methods for finding roots of functions. Let me review. The first method was the bisection. Advantages, there are actually 2 major advantages. First of all, it always works, it's reliable, because we have the root cornered. And the second advantage is that we have perfect information about the error, or rather we have a perfect upper bound for it, which is enough. Disadvantage, well, it's slow. Theoretical order is 1, so it's a linear method. And then we improved on speed by passing to the Newton method. Now, the Newton method has a theoretical order equal to 2, so for every iteration there is a specific improvement of the error, namely it gets roughly squared, which is very nice. But we pay for it. Newton method is no longer reliable, and we have no control over the error, so we have to introduce stopping conditions which are also not reliable. So all kinds of trouble. Finally, another disadvantage is that this method actually needs derivative, which is not always available. So we passed to the secant method. Now for the secant method, we got rid of the derivative, and we paid for it by dropping the order of the method to the golden ratio, in fact, which is about 1.6. So it's a compromise. We still have those problems with reliability, with control over the error, so in this respect, it behaves very similarly to the Newton method. And finally, we also talked about something like a practical order of the method, because the theoretical order talks about improvement per one iteration. But this iteration is a mathematical concept. It doesn't take into account how much work you have to do for such an iteration. So it's more natural to ask what kind of improvement you get for one evaluation of your function, or something similar to your function, like the derivative. And for the bisection method, this practical order is the same, because for every new iteration, you just evaluate your function once. The same thing is true for the secant method. However, for the Newton method, we derived that the practical order is square root of 2, which is about 1.41. So actually, the Newton method, from a practical point of view, was not as good as the secant method. And now we will ask a key question. These 3 methods, they are actually representatives of 3 different viewpoints, 3 different approaches. Can we use these approaches and make them better, to obtain better methods from them? And the answer is, well, that's an interesting question. Let's have a look at it. Let's start with the bisection. Do we have any ideas how to improve it? Well, let's see. Here is a typical situation for a bisection method. At a specific iteration or a stage, you have an interval, and you know the values at the endpoints. And then we split this interval into halves, and we decide which of these halves we want to take. Let's say that here the value is positive, so the next iteration is this one. However, let's compare it with this picture. AK, BK, we know the value on the left, and let's say that it's here, and we know the value on the right, let's say that it's over here. Now, when I look at this picture, it actually sends to me a specific message, especially if I compare it with this picture. When I look at these 2 values, they suggest that the root is perhaps somewhere close to the middle. On the other hand, with a picture like that, I strongly suspect that the root is somewhere close to this place. And that's the key idea for improvement over the bisection method, perhaps improvement. I'm going to approximate the position of this root using actually the secant line. So I'm using exactly the same formula which we have for the secant method. So I put the secant line here, I find the intersection, and this point will be the new point for my decision making. So I substitute this point into my function, and let's say that it comes out positive. And I say, okay, the sign is changing here, so this will be my new interval. Wonderful. So instead of passing from the same interval AKBK to half of it, we pass to a much smaller size. So this actually seems like a good idea. And this is a method which is called regula falsi. which is typically translated as a false position method, because this is like the false position of the root. Now, when you look at this picture, you may wonder, oh, wait a second. What if the situation looked like this? Here is one point, here is another point, I connected them. So far, so good. AK, BK. And now I substitute into my function, and I find that at this location, the value is negative. Then the change of the sign appears over here, and my next stage is this one, AK plus 1, BK plus 1. So in this case, this regula falsi method is actually better than the bisection, because it gets me to the smaller interval. But if the function here is negative, then it's actually significantly worse than the bisection method, because instead of 1/2, I have almost the whole original interval. So this actually introduces some doubt that perhaps this regula falsi method is an improvement. Perhaps it's not an improvement. Perhaps it's even worse. So let's have a look at it. Here I'm loading the familiar cubic polynomial which we have been using to test those basic three methods before. And I'm actually just now replaying a code that I used when we were introducing and testing bisection. So I'm using the same interval, the same tolerance, everything is the same, and the stopping criterion is bracketing criterion. So we are waiting for this interval to drop below the prescribed level. Here we go. And it seems that in 13 iterations we got the answer. Let me make a little chart. Bisection, regula falsi, and it took 13 iterations. Now, let's try the same settings, but with the regula falsi method. Here we go. And it took 49 iterations. Well, this doesn't look too good. And in fact, I'm claiming that it took infinitely many iterations. Why? Because, well, the procedure actually stopped for a different reason than it usually does. Notice that the test value is still large. And the procedure stopped because it takes those approximations of roots, those x's, which we can see over here in this column. It takes those x's, it substitutes them into the function f, because we need this information anyway, and then it checks whether perhaps it's not 0. And it so happens that at iteration 49, the value of f at this location is 0, so the procedure stopped, and it says, okay, I don't care about your stopping condition. Whatever it is, I see that actually we have the root. But if we were relying on the stopping condition, then the procedure would not stop. And it would never stop. Let me explain why. Actually, perhaps another picture will be better. Here we go. This situation comes from a shape which looks like this. I call it hockey stick. Now, when you try the regula falsi method, you connect. Here is the dividing point, and you substitute into your function, and you decide, okay, the right part, that's where I want to go. So again, you connect. You find your dividing point, you substitute, and you say, okay, this right part is where I want to go. And you can imagine that as you keep going, you always modify only the left endpoint of your interval. You will never change the right endpoint. And the interval that you are getting will be getting smaller, 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 but it will be never smaller than this one, where r is the actual root. Now, the stopping condition for bracketing method, it waits for this interval to be small enough. But this will never happen here with the regula falsi method if your function does not cooperate. That's a problem. Okay? So let me just finish the picture. And let's ask what we can do about it. Well, there is an interesting idea. I look at those points which I've been using, and I notice that they actually approach the root. So why don't I actually drop the bracketing stopping condition, and instead I use, let's say, the absolute difference stopping condition. And that one should recognize that we are actually having a nice convergent run. On the other hand, we know that the absolute difference condition is no longer reliable. So we are giving up a little bit. Let's see, let's compare. I go back to my bisection method, and I change the stopping condition to absolute. So now, we just need 12 iterations for the bisection method. And I'm going to run a regula falsi method, again with absolute stopping condition, absolute difference, and it took 18 iterations. And now you can see that the testing value was decreasing until it dropped to a small enough number. Now this confirms that for a function which is shaped like that, we are choosing the larger part, and therefore it's slower than the bisection method. This we expected. However, a lot depends on the configuration and on the initial data. So I'm going to make another experiment. Let me add heading here. Here the starting interval was 0 and 5. I'm going to change the starting interval to 0 and 3.5. And I'm keeping the same function. And let's have a look what's going to happen. Now for the bisection method, notice that this initial interval is roughly half. It has half the length of the initial one. Not quite, but roughly. So either we will get the same number of iterations, or perhaps it will decrease by 1, because we are saving some time for the bisection method. We will see. Okay, 11. So there is an improvement of 1 iteration when we start from such a smaller interval. And let's try the same thing for the regula falsi method. And it took 9 iterations. And suddenly, just by changing the initial interval, the bisection method is slower than regula falsi. So they are really comparable. It all depends on very fine situation, on very fine details. So when it comes to theory, it turns out that regula falsi also has both theoretical and practical order 1. So this is not really an improvement over bisection. And it takes more work to figure it out, so why would we use it? Still, it's an interesting idea. And sometimes people use it for all kinds of reasons. But this is not the end of the story. When you look at the problem which the regula falsi method has, you notice that it's indicated by the right endpoint never changing. You can see it over here in the list. The left endpoint changes, and the right endpoint stays the same. So you can use this as an indication that the regula falsi method met a function which is not really friendly. Can we do something about it? Here is an interesting idea. You keep track of changes, and you notice that the right endpoint stayed the same for several iterations. Let's say for 2 iterations in a row. And then for the next iteration, for the third one, you decide to artificially reach in and sort of mix up the situation by lowering the right value. You divide it by 2. But just for this one iteration, provisionally. So you take this height, you divide it by 2, and now you try the secant. Now when you compare this secant line and this new secant line, you can see that this intersection moved to the right, which speeds up the process, and it also actually increases the chance that the function will be here in between, and you will change the right endpoint. And this often happens with typical functions. So this is a good idea, and this is actually a method, another development of the bisection idea. This is called the Illinois method. Because it was developed by mathematicians from the Illinois State University. And for a typical function, you get 2 runs of regula falsi, and then 1 modified run when you divide certain endpoint, the value by 2. Then you get another 2 runs of regula falsi and a modified step. This is typical pattern. And when this happens, it can be shown that the theoretical order, which is also the practical one, is about, okay, let me put here, is about 1.4. And it's the same as the practical order, because for the next iteration, again, you just evaluate your function at this dividing point. Just 1 evaluation of function is enough. So much for the bisection method, bisection idea. When you are using the Illinois method, you can actually use the bracketing stopping condition, so you have control over the error. It's reliable, and still it's fairly fast. It's actually almost as fast from practical point of view as the Newton method, which is wonderful. Okay, let's have a look at the Newton method. Can we improve on it? Good idea. Comes right here. The original Newton method works like that. You are sitting at some place, xk. You know the value of your function, and you decide to approximate the root using tangent line. So the original Newton method uses, in fact, Taylor polynomial of degree 1. And when you use Taylor polynomial of degree 1, you get order 2, which is the theoretical order. But then you ask, how much work did it take? And you have to evaluate f, you have to evaluate f derivative, and therefore the practical order is square root of 2. And let me emphasize that it's a square root. What happens if instead of Taylor polynomial of degree 1, we use degree 2? Well, from the picture it would seem that this could work much better. Can we do it? Well, we can figure out f, we can figure out f prime, and also f double prime. This is no problem if the function is differentiable, if we know the formula. And it can be proved by modifying the proof that we saw before, that the order of such a method would be 3, theoretical order. However, now we need 3 evaluations. So what is the practical order? That's a very good question. Well, let's have a look at it. We have error ek, and theoretically we make just one iteration, and the new error should be something like c ek cubed. But when we measure it from the point of view of work, we first have to figure out f. Then we have to figure out f prime, then f double prime, and then we get the answer. And there is this imaginary working order or practical order. And the original error, when we make the first step, changes into ek to power q and times some constant. Let's not worry about the constant. Then we use another function calculation. We are figuring out the derivative. So we get to the second stage. And again, this error, which is here, gets raised to power q, which brings us here. And then we do another function evaluation. So this is like another imaginary iteration happening. So again, the error, which we have here, gets raised to power q to get us here. Now, how much is e to q to q to q? Well, you work it out. This is ek to q cubed. When we compare practical and theoretical point of view, we can see that q cubed is 3. And therefore, q is the cubic root of 3. Can we use cubic Taylor polynomial? The answer is yes. We could use T3. The theoretical order would be 4, and the practical order would be 4th root of 4. So let's put it here. The Newton, when using T1, tangents, has this data. When we pass to Newton with T2 with quadratic Taylor polynomial, then theoretical order is 3, and the practical order is cubic root of 3, which is about 1.44. And this is where it gets interesting. We do much more work because we have to figure out all those derivatives and things like that. And the practical improvement is almost negligible. So is it worth it? Well, definitely not if I add another piece of information. How do we get the next approximation? The answer is we take the Taylor polynomial of degree 1, 2, whatever, and we find its intersection with the x-axis. Now, for tangent line, this is almost always okay. The only difference, the only exception is when the tangent line is horizontal, then we are in trouble. But otherwise, we easily find the next iteration xk plus 1. But now imagine that you are working with quadratic polynomial. So we are sitting here. You figure out the quadratic polynomial, and it may easily look like that. And you have no intersection. Or it may look like that, and you have 2 intersections. Which one are you going to choose? Well, actually, there is no rule of the thumb that would help you, really. This is a big problem. So it's not just that the improvement in order is negligible. You also suddenly introduce big troubles by passing to a quadratic polynomial, quadratic Taylor polynomial. So this is definitely not worth it. Actually, sometimes, in real exceptional cases, people did use this quadratic Newton method. So it has a name, which I forgot because it's not used almost at all. So this is not a total blind alley, but it's almost a blind alley. Let's not follow it anymore. So we are not going to be really interested in this one. Okay? We will be comparing bisection, regula, falsi, Illinois, Newton, secant, not this one. Not really interesting. Let's make some room and let's ask about improvements to the secant method. Let's start by recalling the idea for the secant method. We have two values of our function at two different points. Let's say this is xk, this is xk minus 1. This is value fk, fk minus 1. So we put a secant line through these 2 points, and this will be our new xk plus 1. We know fk minus 1 from the previous iteration, so we just calculated fk, the value here, and we got the answer. So that's why the practical and theoretical order agree for the secant method. Why don't we try to put through a quadratic polynomial? For a quadratic polynomial, we need actually 3 points, but we have perhaps the previous one. So while the secant method uses information about past and present to get us to the future, the quadratic method would use information from xk minus 2, xk minus 1, xk, and move us to xk plus 1. So quite naturally, this would need 3 initial guesses, unlike the secant method where 2 initial guesses are enough. Well, let's try some picture over here. This is xk minus 2, this is fk minus 2, and we put parabola through this, and we hope that the next iteration will be better. Let's see. How does it actually work? Can we efficiently construct a function which passes through 3 points, a quadratic polynomial? Well, we had this lecture about interpolation, and that's probably the easiest way. So how does it go? The interpolating polynomial P2 will be composed of 3 parts. Each part will be based on 1 point, let's say on this one. So the value is fk minus 2, and we multiply it by a special Lagrange polynomial. Then the next one is based on fk minus 1, and again Lagrange polynomial over here. And the next one is based on fk, and again Lagrange polynomial over here. Now those Lagrange polynomials, if you remember, they look like this. 2 factors for 3 points. And in those factors, there is always x minus. And here we put the points that we have in our partition, but not the one that we want. This is based on k minus 2, so this point is out. And this guy comes here, xk minus 1. And this guy comes here, xk. And now this guy makes an appearance over here in the denominator. So that would be the Lagrange polynomial for the location xk minus 2, and similarly we construct the other Lagrange polynomials. We talked about it. So this shows that the calculation is not all that friendly. We need to evaluate the function just once to get fk, because these 2 values are known from previous iterations. But then to work out the data, this is actually quite a bit of work. The good news is that this method has order, theoretical and practical, about 1.8. It's called quadratic interpolation. The bad news is that we still have the disadvantages that we saw with the Newton method with quadratic Taylor polynomial. So it may easily happen that this quadratic polynomial does not intersect the x-axis anywhere, or it intersects it at 2 positions, and then we don't know which one. And also finding the root is not all that pleasant. However, people had this interesting idea. Let's have a look at the situation again. And this time I will be more careful in my notation. So I have points here, here, and here. xk minus 2, xk minus 1, xk. And with these I have values fk minus 2, fk minus 1, fk. And I have this problem that if I construct a quadratic polynomial, then it will be like that. This is P2, quadratic polynomial. Here comes ingenious idea. Let's pass to inverse situation. So I'm changing the role of the variables. Y is now independent, X is dependent, and these points, they also transform. I have to be careful now. So, one here, one here, one here, one here, one here, one here. This point is called fk minus 1, and it is sitting somewhere here. Somewhere here. This point, the middle one, is called fk, and is sitting, well, it's sitting over here. And finally, this one is called fk minus 2, and it's sitting close, it's sitting here. So let me just imagine this turns around and becomes this. Is that right? I think so, yeah. So that's the mirror image when I'm mirroring around the main diagonal. Okay, now this is a situation when I can actually construct a quadratic polynomial. Let's call it p tilde, but now this takes y as the variable. And it goes like that. Now remember, we were interested in intersection, but with what? With the x-axis. So we are really interested in this point. Now, first advantage is that there is just one intersection. It can never happen when you have a polynomial that it would intersect the dependent axis at more than one place. And it will intersect it at some place because this polynomial exists for every y. And the second advantage is that you get this intersection easily. You simply substitute 0 into your polynomial. So when you substitute 0, you get xk plus 1. That's how easy it is. How do you construct p tilde? The answer is you use this formula, but you change the role of xk and fk. So there will be f's over here and x's over here. This is the only difference. So you can recycle the formula. It's not easy. It's not a simple formula, but it does work. And you remove all the troubles, because now, by switching around the main diagonal, passing back to the original picture, we now have a polynomial that goes like that. And here is the intersection that I want. So that's the polynomial p tilde. Okay? This is called inverse quadratic interpolation. And the theoretical order is about 1.8, which is the same as the practical order. So this is definitely, from practical point of view, better than all the methods that we have here. It does not require any derivatives. Of course, it's not reliable, because it's not a bracketing method, but it's a fairly good method. There is one little problem. What happens if two of those points have the same y value? Then we are in trouble, we cannot continue. So yeah, there is a trouble also here. You can imagine it like that. 3 points, and these guys have the same value. When you change it around the diagonal, you will get this. And of course, there is no quadratic polynomial which passes through such points, because you can never have two values at the same location. Okay? So there are some troublesome cases one has to worry about. How does it work? The answer is quite well. Let's make an experiment. Again, here is our familiar cubic polynomial that we want to use for testing, and I decided to use initial values 3, 4, and 5. Why not? I just, made a guess. And in 7 iterations, I got to the answer. So if you remember, bisection needed something like 11, 12, regula falsi also. So this inverse quadratic interpolation definitely seems to be better. I am not going to use it in comparison, actually, because now we are reaching this interesting idea. People like the idea of inverse quadratic interpolation because it's fast, it does not need derivatives. It's a very nice method, but what they really were sorry about is that they are losing the bracketing advantages. The bracketing methods with this control over the error, reliability, everything. So there was this idea to combine these methods. Here is how it goes. You have an interval ak, bk. And you have data about your function, fk fk, one of these will have -1. Well, there would have to be some adjustment in notation. One of them would be xk, another one would be xk minus 1. So let me put it this way. There are little technical details one has to worry about. Now, based on this data, I could try the bisection method. I could try the regula falsi method, which is actually the same idea as the secant method. So we get bisection, we get a secant cross regula falsi. It's the same formula, and we can try inverse quadratic method. And we get 3 candidates, because there's also a third value from the previous iteration floating around somewhere here. So we use these 3 ideas to get 3 dividing points, D1, D2, D3. They are floating somewhere around here in this interval. D1 comes from bisection, from the secant formula we have D2, and from the quadratic inverse some D3. And then the trick is to choose wisely which of these points you want to use for the bisection idea, which means you take the point, you substitute into your function, you get value, and you choose the part where the sign changes. Okay? So the framework, the basic framework is the bisection method. We have a bracketing method with control over the error, but the choice of the dividing point is actually a mix between bisection, regula falsi, and inverse quadratic interpolation. The problem is that you cannot do it for every iteration by looking at it and comparing. You have to invent some way for the computer to decide, and this is definitely not easy. There is a guy called Brent who in 1973 published, I think in 1973, published a method where he introduced some tests. And they are not easy. When you look it up, these are quite complicated tests. But these tests worked rather well. And in this way, the guy got a method which is bracketing, which means reliable, but it is also better than linear. Precise order is hard to determine because you never know what's going to happen. It depends on the function, on the starting interval, things like that, because you are actually using methods of different orders. Secant is about 1.6, this one is about 1.8, this one is about 1. Okay, so all kinds of trouble can happen. But the Brent method is definitely better than just bisection. And this Brent method was deemed to be so good that it became standard. So in many software packages, when you just say, find me root of this function, and you don't specify how, they just use the Brent method. And it is still true today. However, people try to improve on it, of course, because those tests are really difficult. And in 1997, I believe, there is a guy called Chandrupatla, and he invented a significant simplification. First of all, he does not use the secant method. He just dropped it. He just uses bisection and inverse quadratic method. Second improvement is that he actually decides before calculating those dividing points. For the Brent method, you calculate all 3 dividing points, which is a lot of work for the inverse quadratic. That's this formula. And after you have these 3 points, you start comparing. The Chandrupatla method, it first decides, and then it calculates just one unique dividing point and uses it in the bisection manner. So this was very nice, and also the test is much simpler compared to the Brent method. So pretty much everything is simplified. And as I said, it is really hard to measure scientifically performance and compare it when the method is mixed, like that. These are mixed methods. So people have to test them on different functions, different situations. And the Chandrupatla method seems to be superior, but it takes time for people to accept it and to test it really properly. But in, let's say, the last decade or so, the Chandrupatla method is becoming slowly a new standard, it seems, because it has been tested as really reliable, a good performer. Because it's a relatively new method, it's not easy to find the algorithm. Especially if you want it in such a way that you can implement it yourself. But it is possible to dig it out, and I have it in my procedure. I can choose it as a method. So let's now make a big comparison of the basic 3 methods, improvement, which means regula falsi Illinois, and Brent method, which is the standard, and Chandrupatla, which is perhaps the top of the line right now, state-of-the-art method. And we will see what happens. So we will be comparing number of iterations needed to reach the answer, essentially. We start with function sine x minus 0.5, which is the sine function lowered, and therefore there is a root which we should know. After all, sine of x is equal to 1/2. The natural root be, how does it go? Pi over 6, I think. That should be it, okay? So we know the answer, we can control the error, things like that. Let's see. So, bisection. The bisection method took 50 iterations, which is quite a lot, especially compared to our previous examples. And the reason is that I actually made the tolerance much smaller. I now ask for a much higher precision, so the bisection as a slow method had to work longer, quite understandably. And it stopped at iteration 50, which is just in time, because I have a limit there on 50 iterations. If the bisection method did not succeed in iteration 50, then the procedure would stop anyway and complain that this is useless, I should try something else. So that was lucky for the bisection. Regula falsi actually liked this example, and it provided the answer in 15 iterations, so this is much better than bisection. Got lucky, regula falsi. Illinois, which is the modification, was still faster in 8 iterations, and you can notice this m means that we did modifications. And I talked about it. Notice that m is used every 3rd iteration. That's the modification when you artificially decrease the value at the endpoint. Secant. Secant is a method of higher order, 1.6, so we expect something nice to see, and we see 9 iterations, which is actually slightly worse than the Illinois method. So the Illinois method is quite good, really. Newton, well, Newton is our favorite, of course, with order 2, and in 7 iterations, it probably found the root, which is also wonderful. But now we have to think about this. For every iteration of Newton, we need 2 evaluations of f. So in fact, when it comes to work, this is more like 7 times 2 is 14 iterations. So from practical point of view, Newton took more work than Illinois and secant methods, and comparable to regula falsi in this example. Okay, so for Newton, we have to really double if we want to see the work. We have to double the number of iterations. Now, Brent method. Brent method needed 7 iterations, which is about as good as Newton. And these are actually even practical iterations, so it is a good number, 7 iterations. And you can see that it was mixing up secant method and inverse quadratic. SQ, SS, this denotes the method which was used at that particular step. And finally, Chandrupatla needed just 6 iterations, so it's the king of them all. And it was using the inverse quadratic interpolation with the exception of the first step. In the first iteration, it used bisection, and then it used the super fast inverse quadratic interpolation or inverse quadratic method. So Chandrupatla wins here. Let's have a look at the next example. 1 over x minus 0.25. How does it look like? 1 over x is the hyperbola, and I'm lowering it. It looks like that. Where is the root? The root is 4. So, well, let's have a look. I will load the data, and I will go back to my code, and I will just ask all the methods to work it out. Let's see. Bisection, 28 iterations. Regula falsi actually did not get there. It exceeded the number of iterations which is allowed. So in this case, it's the bisection which wins. As I said, bisection, regula falsi, depends on the situation. They are comparable on average. Illinois, again, very good. And modification, well, there's actually quite a few modifications when you look at it. So it was modifying the value at some endpoint, and it didn't help because this point never changed after modifications. So it kept modifying until finally it moved. So yeah, this was not an easy example for the Illinois method. Secant method, our favorite, of course, without derivative, 10 iterations, quite good. Newton method, 6 iterations, which is to be expected because theoretical order is 2 compared to 1.6 for the secant method. But the practical order of Newton, I have to take 6 multiplied by 2 is 12, which is worse compared to secant. Brent this time took 1 extra iteration compared to Newton, and again it is preferring the secant method and the quadratic method, inverse quadratic, for determining the dividing point. But there is an equation when it also used bisection, the middle of the interval to divide. Chandrupatla is again the king, formally the same number of iterations as Newton, but less evaluations of functions, and it was using bisection twice and then inverse quadratic interpolation. Very nice. I think we are beginning to see that the Chandrupatla method is really nice. Okay, another example. Let me run the methods. Will there be something interesting? Well, again, bisection had trouble here, and regula falsi was better, Illinois still better, and again here we see the familiar pattern. Every third iteration is modified. So this is typical. The secant method, it's actually a bit slower compared to Illinois. One extra iteration, but still okay. Newton method, theoretically the best, or the better than secant, but practically 10 iterations is worse. Brent, this time, the same number of iterations as Newton formally, and again it is mixing up secant method, inverse quadratic, Chandrupatla, the king. Okay, so far Chandrupatla is really the best. Let's see whether it can last through some other examples. Cosine x minus x, that's a nice thing. So we're really looking at intersection between cosine and x, the diagonal. These are nice functions, so we do not expect any trouble. I will load the data and run it. Okay, bisection slowest, regula falsi faster, Illinois still faster. I mean, there is really nothing new here. Everything seems to be working as expected. Measured by number of iterations, this time the Newton was faster than Brent and Chandrupatla, interestingly enough. But as we know, Newton needs more work. So practically speaking, 10 evaluations for Newton. So this time Brent and Chandrupatla, they came up even interesting. Now, let's move to something really, really interesting. We know that for roots of higher order, the order of methods tends to drop. For instance, Newton has theoretical order 2 for simple roots, but when the multiplicity is higher, it drops to 1. And that's exactly the next example, cosine x minus 1. So we have a function which is the cosine function lowered by 1. It looks like that. Obviously, there is a root here, and it is a root of multiplicity 2. And let's see how it impacts the performance. And what you can see here is a lot of complaining. Why are those methods complaining, and which methods are complaining? That's a good question. The answer is bracketing methods are complaining, because as a root of even multiplicity, we cannot find a neighborhood where the sign of our function would change. And if the sign doesn't change, bracketing methods are out. You can see it in the picture here very nicely. So all the bracketing methods, they actually fail. And what we see here is the secant method, which was so slow that it actually exceeded the maximum allowed number of iterations. And we see the Newton method, which eventually got to the root in the 50th iteration, which is the last which is allowed. It finally found the root. It was really extremely slow. Let me go, if you want to compare, for some root of multiplicity 3, because for a root of multiplicity 3, you are going to have a change of sign. I'm going to use cubic function. I just shift it so that it's a little bit more interesting. So the next test function will be x minus 1 cubed with the obvious root number 1. And now also the bracketing methods will work. So we get an interesting comparison. Well, it will be long, because we will see long runs. So this time the bisection method is actually fairly good. You can see 26 iterations, much better than regula falsi, which failed. Illinois method kept modifying all the modified steps. After 47 iterations, it finally got close to number 1. Secant method really reacted badly to root of order 3, and it never reached the answer in time, but it got actually fairly close. I think one more, perhaps 2 more iterations, it would get there. But, okay, failure. Newton method. For a root of order 3, it's really bad. 41 iterations. So who is the king so far? So far, the king is the bisection method with 26 iterations. Brent method. 30 iterations. And notice how often it has to use the bisection method. because the quadratic method, the secant method, they are really bad for this root. So it's using the bisection method to speed it up. And finally, Chandrupatla in 21 iterations. Again, lots of bisections, but notice how it uses inverse quadratic steps at the moments when it's really good. So the strength of the Chandrupatla method is in smartly choosing when to switch between inverse quadratic and bisection modes of operations. And it does it in such a good way that it actually beats even the bisection method. 21 iterations, this is better than bisection with 26. So the Chandrupatla method really shines for roots of higher multiplicity. Let's try it with something less obvious. I have here a function, the last one, and it's sine of x minus x. Now the function sine of x minus x, it has a root at the origin, at 0, and it is quite obvious to people who actually know the Taylor expansion of the sine function that here the root has multiplicity 3. So the bracketing methods should also work. Let's have a look at it. So how close did they get and how quickly to the root 0? Well, the bisection method took 27 iterations, which is comparable to the previous run. Again, for root of cubic multiplicity, this is respectable. Regula falsi failed. Illinois, it got there at the very last moment, 50 iterations. So again, bisection is better. Secant failed. Newton didn't fail, but it needed 45 iterations to get there. So again, bisection wins. The Brent method failed, although it got really close when you look at the number there. It's almost there, but not quite. Chandrupatla, 18. Again, bisection was king so far with 26, I think. Chandrupatla, 18. This is much better. So this confirms that this Chandrupatla method seems to be the king of the hill so far. And we will see how it develops, whether it really becomes the standard, industry standard, or perhaps something better will come along. We will see. So that's it for today's lecture. I hope you enjoyed it. It's really, at least for me, it's really nice to see how things actually work with real problems, testing them, playing with them. Lots of fun. So in the next lecture, we will actually still try to find solutions of algebraic equations, but we will use a totally new approach. So stay tuned. See you next time.